and using which you understand, right, whether a motor is getting overloaded, motor controller is getting overloaded. And as soon as you see there is some overload phenomena happening, what you do, you restrict the operation. So even though the driver is trying to give higher torque, higher speed command, you will restrict, because you want to control in a safe zone. You don't want to damage them, right? So that kind of protection feature is what we kept in the vehicle. Sometimes what happens is driver suddenly gives throttle, and that gives us jerky motion in the vehicle, right? So we give some smoothing function in our controller so that it is more smoother. Another very interesting feature is that fault status monitoring and display. So these are all electronic systems, and sometimes there definitely will be some of the other fault. But then you go to a technician to repair those, but the technician does not know where the fault has occurred, right? So if you could give the technician some idea that a fault might have occurred, so it will be easier for him or her to find out, right, where the fault has occurred and easily repair it. So that kind of indication we are providing in our motor controller. I'll show you a demonstration also. So what happens is that we made a list of around 26 faults, and once any of these faults are happening, we are showing some error code in the display. So looking at the error code, the technician gets to know that there some fault has occurred, right, and then he or she can repair it. And then we provided regenerative braking in our system, and we provided a customized display also. So these are some very summary of what are the additional features that we have provided in our solution. So let me show you a very short demonstration video on this, and then I can. So this is that VLC motor that our team has designed, and this is the motor plus vehicle controller together in a single package, right? That was again industry first feature in the category. And then we integrated with entire things in the vehicle. We had to integrate with the brake because we had regenerative braking, right? And then we tested on road with 4 passengers. We went forward, backward with some gradient. And then while running, we were showing some display also. So here, it may not be very clear to you. I'll show you a clear display later on. This is an example of that fault status demo. Of course, we did not show it on road, right? We created a situation during a demonstration. So what you can see is that, just a minute. So this is how a display looks like when it is healthy, right? So I'm not sure whether you can see it clearly. In the middle, it is showing what is the speed currently the vehicle is having, what is the SOC of the battery, state of charge. It is showing what is the remaining range. So currently it was showing 30 kilometer, and driving mode, so that is forward, reverse, those kind of things it was showing. So this is how the display looks like in a healthy state. As soon as it sees some fault, you can see the display changes. Okay, so the display is showing some fault along with the fault code. It is not very clear in the video. I'll show you an image. So basically, it's showing an error code of 16, ER_16. So we have a list of error code. So when I say ER16, I understand that there is an under voltage happened. So basically what happened is that the battery voltage, which was supposed to be 48 volt, we made it around 38 or something. So as a result, our motor controller detects that, right, that there is an under voltage fault. So then we have to clear it, right? So you can see one of our technicians is clearing that. And once it is made around 48 or so, we could run the system again. So again, the system become healthy, right? You can see the display changed. So there is no fault message. So that's how, using a simple error code, you can communicate with the technician where that fault has occurred. So that kind of techniques or that kind of features are incorporated in the particular solution that we offered. So on this line, and this solution has several other benefits also, right? Our motor was more efficient, overall package was more efficient. The temperature profile was also much stable and within much lower range as compared to the off-the-shelf solutions and all. But only one problem currently, these whatever we develop, these are all slightly more costly than ready-made products, right? One major reason is that for motor rare earth magnet, we have to get it from abroad, right? Semiconductor devices, we have to get it from abroad. We don't have any direct low-cost solutions available. So the component that we have designed our system with, these are costly, right? And of course, we don't have bulk place order, so our cost is definitely on the higher side. So as a result, these are having much better features, overall better efficiency, but then cost is definitely higher than the off-the-shelf solutions. So this is some of our development in this field as an example. I'll just talk about another important project and then I'll wind up. So this is one of the projects that is still ongoing. It is very close to end now. So in this project, what we did, basically same e-rickshaw. So currently what is happening is that you connect a single motor, and this motor is distributing power to both the wheels through a device called differential. That also we discussed earlier, right? Problem with the differential is that it is taking power through it. It has to go to both the wheels, right? So basically, as you know, any component you put in the cascade or series path, it affects your efficiency, right? And also this mechanical differential has its own wear and tear problems. It needs maintenance. So to avoid that, we came up with a solution called e-differential, electronic differential. So idea is very simple. You throw out the mechanical differential, put 2 hub motors directly on the wheels. Okay. So basically, you are putting 1 hub motor on the wheel and 1 hub motor on the other wheel. So you have 2 hub motors, you have 2 motor controller, you have to control 2 motor controllers in a synchronous manner, right? So that is the whole idea, and there are so many other research projects that is also going on under my team. I'm not going into detail due to shortage of time. So let me just show you if I can do it. So this is an example of that product that I was referring to. So basically in this wheel, these are all wheel that you see, these are all motorized wheel. And this is the differential unit, but actually inside it there is nothing. We took out the differential. So we are doing retrofit solution. Inside this differential, the mechanical part we thrown away. Okay. So both the wheels, let me repeat again, these are motorized wheels. We basically have a BLDC motor in the wheel itself along with this braking arrangement. So then we did our own motor controller, our own data logging and all, and we could run on the road also using this. So that was one of the interesting thing that is quite close to completion now. We have filed 2 patents also around this. So basically we took turns in left, right, sudden turns and straight road with passengers, all the things that testing we do on road. So that's what I was saying. Some of you were mentioning that how can you join our project. These are some of the example of development project that we keep on doing, and we get some funding for them also. And if you're interested, you can join them. But of course, we would also expect something from your side. Like sometime, for example, this his name is I think I shouldn't disclose the name. So he was one of our other project staff. He had BTech degree, and then he joined us. Right. Of course, there was some interview and shortlisting process. So we found him suitable. He joined us, and he did wonderful work for us. And eventually he could succeed, and eventually he joined our master degree program also. So after that, he got a very high salary package also. Fortunately, it was a happy ending story for him and us also. Right. So let me close on this. If you have any question, let me know on this. Right. So, Mr. Ashu, you had a very good point. You can sell this motor design to bigger motor manufacturer with royalty if your team is not having volume for bulk production. My team is not having volume for bulk production, of course. And this all technology, what I'm saying, these are all available for licensing. But then, of course, we are not good at advertising and selling. But yes, this motor that I showed, it is certified from ICAT for 2 certifications, right? But again, I don't know, cost-wise, we may not be able to beat Chinese product. But if someone of a bigger company, they're ready to take up this, because we don't have the capacity to manufacture in bulk order. Right? We are an academic institutions. And our industry partner, they're also not a very big company. So if you know someone who may be interested, because we have regular motors, we also have now that hub motor for which can be used for 2-wheelers also, right? So in fact, we can design some customized motors also, customized motor controller also. So if someone is interested, we can do some joint product development as well. There is another question: what type of battery you use? So for e-rickshaw, this particular segment, they use lead-acid battery, right? In some of our project, we use lithium-ion battery also. So we generally get off-the-shelf batteries. My team is not designing any battery as such. We get the ready-made battery. We design motor controller. Sometimes we design battery charger. My team also design solar charger for electric vehicles, right? So if you put solar panels on different sides of the vehicles, how do you control them for better efficiency? Those kind of solution we provide. So there is a question, sir, give me your number. So just note that I talked about only 2-3 projects. We all, of course, have multiple projects in the team. So I cannot share my number immediately. You can just write to me an email if you're interested. So this is my email ID. You can reach out to me if you want to know more about them, right? Okay, how many batteries are used in your project? So e-rickshaw, that vehicle I told, right? This uses basically 48-volt lead-acid battery system. And they generally use 4 batteries in series. Okay, 4 12-volt batteries in series. So in total, 48-volt battery bank. There is again a question: can we get e-rickshaw list of all child parts with specification and photos? This, I think some of the information are available in Amazon also, right? If you want to know more about our products, you can write an email to me. I'll be able to share, which I can share freely. For technology transfer, of course, there will be some fee involved in that. Okay, there is another question. 2 inverter you are using in your system with master slave concept or other. So basically the 2 inverter, both of them for us is kind of a slave, and there is a supervisory controller which is master. So a simple thing, see, when you're doing steering control, right? One of the motor has to rotate at higher speed based on where you're going, right? So based on that steering angle, based on the vehicle dynamics, your estimation, etc., there will be supervisory control that controls both the inverters. So there is a 2-level hierarchy in the design. But that's a very interesting project and a lot of things to learn from this. So someone of you, Mr. Rudra, you said, sure, whatever email you're sending, I'll check them in my free time and I'll get back to you. Okay, there is a question, why in MOSFET numbers in VSI are random, not in serial? These are not random, these are done with a purpose, okay? If time permits, I'll answer this with the BLDC control. Give me 10 minutes, I'll come back to this question. It's a very good question, I'll get back. Any other question, anyone? In case anyone has sent me an email, I'll check it, no worries, I'll get back to you. So I think other questions are answered. So let me talk about 2 important questions that last class someone also raised, and today also some of you are asking effectively. So let me take up quickly. Why? So there are 2 questions that I want to take up. Okay. So one question is, you see the number of the switches 1, 3, 5, 4, 6, 2. These are done in a purpose. Okay. For example, in a BLDC, the switching that we used, that is 120-degree conduction. In a PMSM, we did sine PWM strategy, right? They are not same. I hope you are getting the point. The switching strategy itself is different. Okay, how? I'll tell you. So in BLDC, 120-degree conduction means, see, in BLDC what happens, again, I'm not going to that detail. So in BLDC, the back EMF of each phase, it looks something like this. This I discussed in a previous class also. So for example, this is, let's say, for phase A back EMF. Okay, this is how it looks like. So the current that we are going to say in this case, IA, it will be like this. This is very interesting feature in BLDC. Okay, for PMSM you must have seen the current was sinusoidal, right? But BLDC we never give sinusoidal current. We give this kind of current. So this is going to be the current in A phase. Okay. So what happens is that, see, this duration is one complete cycle, right? This is 360 degree. And this duration, this is actually 120 degree. Similarly, this duration, when you are sending the current, that is 120 degree. Okay. So when you give this positive 120 degree current, this duration, what happens is that you will see that we basically try to turn on S1. And during that second period, we generally going to turn on S4. That is how you give current. Okay. So let me again reiterate this part. This is your IA current. Okay. So when you want to give positive current, you give current like this, isn't it? And when you want to give negative current, that means current should flow opposite direction. So then we turn on this bottom switch. Okay, S4. I hope you could relate it, right? So positive current through S1, negative current through S4. Okay, in simple terms. So each of the switch, theoretically, they conduct for 120 degree. So for entire 360 degree cycle, each switch conducts for 120 degree. Inside that 120 degree, again we do PWM, that will come later if time permits. But theoretically, each of the switch for maximum, it conducts for 120 degree. That's why it is known as 120 degree conduction, right? Now, so similarly for B phase and C phase, those switches will also conduct for 120 degree, okay? And interestingly, in this particular BLDC, you will see that two switches conduct at any point of time. That is the unique feature of BLDC. In PMSM, 3 switches will conduct at any point of time. BLDC controller, 2 switches conduct at any time. That means you will have current in 2 phases. The third phase current is going to be 0, ideal, okay? So the third phase current is going to be 0. This is distinctly different in BLDC and PMSM. In PMSM, all the 3 phase will have current simultaneously. But in BLDC, any 2 phase will have current. Basically, one current will go, same current will come back. Third current will be 0, okay? So after some time, it will be opposite. Like from A phase current is going, it is coming back from B. A phase coming back from C. Then current will go from B, it will come back from C. I hope you're getting the point. It will be just combinations, right? So any 2 phases will conduct at a time. One positive current, one negative current. One is going towards motor, through another winding, it will come out. But the third leg, it will be always off. And this will go on cyclically. So eventually 2 switches conduct at a time. One from top plus one from bottom. What do you mean? One from top means either is this 135, one of them, and one from 462. So one from top category, one from bottom category will be conducting at any point of time, not 3. In PMSM, 3 switches will conduct at a time. Okay? So since 2 switches will conduct at a time, you will see that very interestingly, the switching sequence becomes something like this. First, switch 1 and 2 gets turned on, then it becomes 2, 3, 3, 4, 4, 5, 5, 6. Okay? 1, 2, 2, 3, 4, 4, 5, 5, 6, and then 6 on. And again, 1, 2. So this sort of sequence, to get them this nice sequence, these switches are numbered in this particular fashions. Okay. So this nice sequence you'll get only when you number those switches in that 1, 3, 5, 4, 6 2 fashion. Otherwise you won't get it. Right. So this is the sequence we follow in BLDC. And each of these are for 60 degree. So basically each 60 degree time, one switch will change its on-off status. Other switch won't change. So for each of the switches, you can see individually they will be conducting for 120 degree. So this is for 120 degree, 60 plus 60. Similarly, switch number 3, you can see it is again for 120 degree. But then for each 60 degree, one of the switch will change its states. All these things are decided based on Hall sequence positioning. Okay. So let me give a brief idea about this BLDC if time permits. I'm not sure whether I'll get time. It's already close to 10 p.m. So just 2-3 minutes, I'll tell you what actually we do in BLDC, right? Okay. So basically, you can see this inverter, right, is a very interesting device. And if you want to learn, there are so many things to do. And as I told multiple times, these all subjects are actually semester-long subjects, and if we have to make something harder, it takes a lot of effort. So simply, if I call this is also named as 135. In this, you can relate by AH, AL. Okay, just different name given in this slide. So AH means for A phase, the higher switch. Okay, and A phase, and for this one, A phase, low switch. Okay, high low high low. And here you can see these are the three Hall sensors data. Okay, so Hall sensors, as I told in BLDC, there are three Hall sensors. Each of them will give you just on/off signal, right? Digital signal, 1 or 0. And so ideally for 3 Hall sensor, you're supposed to get 8 combination, but then all 0 or all 1, that will never happen because of their placement. So effectively you have 6 combinations. Out of 8, 2 are ruled out, so you are left with 6 combinations, right? And based on this 6 combination, which switch you want to turn on and off, that simply comes from this truth table. For example, if your Hall sensor status is Hall A is high, Hall B and Hall C are low, so then A phase top device you turn on. So this will be turned on, okay? Then A phase, see other are 0, only C phase low, that will be turned on again. So these two will be turned on for this sequence. All other switches are turned off, okay? So this is how one of the answer that I gave. Hall sensor or any position sensor in the rotor, these are responsible to eventually deciding your switching states, directly or indirectly, okay? So here at any point of time, you can see only 2 devices will be conducting. So 1 means on, 0 means off. This for BLDC, okay? So it is not same as your field-oriented control. That was completely different, right? Here, based on your Hall sequence, you are going to turn on and turn off which switches, okay? So I hope you got some idea about what is done in the hardware or practically, okay? Is there any other question from your side? Otherwise, there was one question left from the last class. So I'll take up that. Quickly, I'll take up that. The question was that why we are using the capacitor at the input side that I did not disclose yesterday. So quickly, I'll take up that. Just give me 2-3 minutes. So there is a question yesterday last, it was asked why we use this capacitor. Okay. So there are 2 main reasons. I'll try to make it quick, we don't have much time. One is physically when you put the motor controller, right? And when you place the battery physically, location wise, there will be long wire connecting them. In circuit diagram, you see we show battery and a motor controller very close to each other, right? But reality, what will happen? Your battery may be in some place, your motor controller may be in some other place. So there will be a cable connecting them, right? It is not, they are very close to each other. Now you can say, how does it make sense? That makes a huge sense in hardware, okay? You may not see it in naked eyes. So what happens is that due to this long cable, I'll make a simplified version for you. Let's say this is a long cable and there is a switching happening. A simple circuit I'm taking for time being. Okay. So ideally, when the switch is off in this circuit, the voltage across the switch, okay, just let me take the motor controller circuit so that you can get correct relevance. In the motor controller for each of the phase, we have 2 switches, right? S1, S4. So when S1 conducts, right, current flows like this, and voltage across S4, it will be off. Okay, and then next state, what will happen is, S1 will be off and S4 will be on. And current will continue flowing in this. So the voltage across this S1, it will be same as the VDC. Right? That also we discussed in our previous classes, KVL if you remember. So that's how you decide the voltage rating of the switches, right? So basically when this S4 is on, voltage across it is 0, right? So then voltage across switch is same as VDC. So this is very straightforward. This is what we teach in theory. Okay. Now what happens is that practically when you connect a battery with a motor controller, this may be a long cable. Now what is the problem with long cable? Any physical cable, it will have some parasitic components. Okay, unwanted. What? It may have some resistance. It may have some inductance. Very long cable may have some capacitor also, right? So if it has some resistance for a long cable, practical wire will have some resistance. What is the problem? It will have some additional loss, not a big deal, okay? But the inductor, you may not see it, right? Physically, you see there is a cable, where is the inductor? But those who have taken electrical engineering course, our long transmission line, we model it using an inductor, right? Any current carrying conductor, it has some magnetic phenomena associated with it, and that gives rise to inductance, isn't it? So without going into all those physics detail, assume that a very long cable, any physical cable, it will have a little bit of inductance into it, because when current goes through any coil, it will have magnetic flux around it, right? So that phenomena gives rise to some inductance. Now problem is that as soon as you have a very small inductance, see this is not deliberately added, it came as a parasitic, right? Inductance. What is the problem? Now, voltage across switch S1 is VDC plus VL. I hope you are getting the point. Isn't it? There is an additional element that came into it. Okay. Now we can say, what is the big deal? Big deal is here. Voltage across inductor is given by L di dt. Okay. What is the meaning of di dt? It is rate of change of current. Okay. Think about it. When this switch was on, all the motor current was going like this through this inductor, right? Let's assume that this current was pretty high, 200 ampere. I'm just assuming. Okay. So when, because in EVs we use motor of 1 kilowatt, 100 kilowatt, 200 kilowatt. I already showed you market survey. So then it will also have a huge current, right? Let's say 200 ampere current was flowing to the inductor. And then when you turned off the switch suddenly, the top switch, current here will become zero because current has no path. I hope you are getting the point. So this parasitic inductor, it has a current jump from 200 to 0 ampere in a very short time because you are using a semiconductor device, isn't it? So this L di dt is nothing but change in current by change in time, isn't it? So it will be change in current is how much? 200. Simple. Change in time could be nanosecond, right? So nanosecond, let's say 1 nanosecond. So that means 1 into 10 power minus 9. Okay. This inductor is also very, very small. Let's say it was 1 nanohenry. 1 into 10 power minus 9. Very small inductor, right? Very. So you can see even they cancel out. Voltage of the inductor is going to be turned into 200 volt. I hope you're getting the idea, right? So for example, for a two-wheeler, you understood battery voltage is 48. Okay. So I can use my switch to be 48. But in reality, you need 48 plus 200. Because that inductor, it will create a LDITT problem. I hope you, in your first year electrical engineering, you have studied that current in an inductor should not change abruptly, right? It needs infinite voltage. So in other words, if you create a sudden abrupt changes in the inductor current, across the inductor, there will be high voltage spike that will come in, okay? So now, voltage across the switch will be, if you apply KVL, this will be this source voltage plus that inductor spike voltage. And that can damage your switch, okay? So what is the protection? What is the solution? Solution is, try to connect a capacitor. The main problem was that inductor was not getting a path for the current. That's why current has to become zero because there is open circuit. So try to provide a capacitor close to switches. Okay. So whatever inductor current it was providing earlier, it will still get a current path through the capacitor, right? So there won't be sudden change in the inductor current. I hope you understood this point, right? So inductor will always get a path, and as a result, your switch will be protected. And capacitor at the same time, it won't change sudden voltage, right? So capacitor won't allow the sudden jump in the voltage. So it will maintain the voltage across it. Okay, that is one of the main reason we put capacitor in the inverter circuit to protect it from high voltage, especially from LDITT spikes. There is one more reason I'll quickly tell without going into much detail. Ideal battery, we show it by this symbol, right? But a practical battery, you know, there will be dedicated battery model coming up for you. You will see that a practical battery, it will have some parasitic resistance, right? And there will be some inductance capacitance also. We call it internal resistance of the battery, isn't it? So when current flows to this resistance, there will be I square R loss in the battery. And as a result, battery get heated up. And it reduces lifetime. Okay? Simple, right? Any practical battery, it will have some internal resistance that you have seen in your first year basics also. So then whenever current flowing through it, there will be I square R loss, and then battery has to, due to loss, it will get heated up and all those problems. Now, think about a very simple, again, same simple circuit. Again, this is a very conceptual problem. I hope you will understand without spending too much time. So, when we have this kind of switch on and off, this switch on and off will happen at very high switching frequency, right? So, if you want to plot this battery current, you will see that this battery current may look something like this, a high frequency pulse. I hope you are getting the point. When switch is on, high current is flowing through the battery. When switch is off, current will become zero, isn't it? So the battery current will be something like this. It is not a pure DC, right? It is a pulsed kind of DC because you're doing a lot of switching in the inverter without the capacitor. You see, I did not use any capacitor. So without the capacitor, the current in the battery will be giving a lot of pulses, high frequency pulses. Okay. So this, if you analyze these pulses through Fourier series, you will see it will have an average value, and it will have those AC, high frequency AC component. You can call them harmonics, simple term. So this is the actual battery current. Okay. So you will see that actual battery current is summation of that average current plus those harmonics, which will be AC in nature. Okay. So what happens is that this is what we want, because battery has to deliver power, right? This is unwanted. So this unwanted component increases the RMS value of the battery current. It increases losses in the battery. It increases heat in the battery. It reduces battery life. I repeat, without that capacitor, what happens? Battery has to give the average current. Average current it has to anyhow give because it has to deliver power, right? So that average current is required. But then this high frequency AC component that goes into the battery, that is detrimental to the battery life. Okay. So to avoid this, principally what we do, we connect a capacitor. So the fundamental remains same. Here we are getting that high frequency signal, right? Here we are going to get only the average, and this capacitor is supposed to provide that high frequency AC part. Okay, I hope you are getting this point. So capacitor protects your battery from those high frequency current which inverter is generating or taking. So logically, battery should provide only the average current which is required. Capacitor is filtering out those high frequency. Okay, so I hope you are getting the point. It will have both I average plus those I harmonics. This is the harmonic current. Capacitor should provide and average current should provide from the battery. So this is how capacitor also protects your battery from additional loss, additional ripple current. Okay. And since capacitor has to carry a lot of those AC ripple current, in practical use, you see that multiple capacitors are connected in parallel, so that their current rating goes up. So I'm pretty sure I've shown you earlier also. Practically, you will see that this capacitor and the motor controller, there multiple capacitors are connected. So you can see these are all those capacitors. This capacitor for 4-wheeler also you see, right? So these capacitors are all connected in parallel, so that they can deliver more those ripple current. Okay. As I told multiple times, capacitor, anything connected in parallel, it increases the current rating. Okay. So they can deliver or they can filter out better those high frequency component. So without this capacitor, you'll see motor controller won't be they won't be designed for practical reasons. But again, in plain eyes, plain knowledge, you won't understand this. These are all hardware related concepts. So with this, it is already 10 o'clock. Let me wind up. Thank you very much for your patience hearing. Those who need any mic access, please raise your hand. As today is my last session, I would like to clarify all the doubt, whatever you have, right? And if no doubt is pending, of course, I'll take leave. And whatever notes I am doing in the class, you must have seen all notes are regularly uploaded in the Google Drive, right? Yesterday's class notes, these are also already uploaded. So what you have to do is just look into the link that I have shared. I don't know, for some reason this link is not operating, but I hope you understand that the same link, whatever I shared in the earlier class, same link, right? Everything is kept there. So please explore that. And I request some of the participants who has the link for the last classes, can you please share it again? So that I remember some of the participant was asking for a link, but I could not provide. I don't know, for some reason this Google Drive account is not available. So those who are getting the link from the previous lessons, please type it in the chat box so that you can share with everyone. Anyhow, this will be shared through your LMS portal again. So with this, I see there are no questions left. So thank you so much for attending the lectures. A lot of time you were very supportive, giving answers quickly whenever I ask something. So that means a lot for me. Thank you very much. And yeah, thank you, Mr. Abdul, for sharing the Google Drive link. So with this, let me wind up. I can see there are no more questions. But again, as I told, if you are stuck with anything, drop me an email. You already have your my email IDs, right? So if you need any